Module 6.1, Logarithms and Exponential Decay. This is chapters 4.3, 4.4, and 4.6 in your book. 6.1 Opener. Many real-world problems involve a rapid type of change called exponential growth or decay. It is often useful to use the properties of logarithms to study exponential growth or exponential decay. Important concepts to focus on. You should remember the relationships between logarithms and exponents and know that they're inverses of each other. They're opposites of each other. Know the approximation for e and be comfortable using it. Be comfortable using technology to model growth or decay problems. Logarithmic functions. Recall that log base a of b equal to c is equivalent to a to the c is equal to b. Again, remember that the bases stay the same. A and a are the base, and you switch these two. You switch b and c. That's what log with a base a of b equal to c means. It means a to the c is equal to b. That's the definition. A logarithmic function is defined to be f of x is equal to log of the base a of x. And a has to be greater than 0 and x has to be greater than 0. Properties of log with a base a. The points 1, 0 and a, 1 are on the graph of the function. So 1, 0 and a, let's say that's a, 1, let's say that's 1. We're on the graph of the function. If a is bigger than 1, then the function is increasing. So if a is bigger than 1, then the function looks like this. If a is between 0 and 1, then the function is decreasing. The domain is between 0 and infinity. In other words, the x values, not including 0, they can get as close to 0 as possible, but they never start at 0. And they go all the way up to infinity. In the range, they can be as small as possible, and they go all the way up to infinity. So again, because the x values can't equal 0, this means that the y-axis is the vertical asymptote. The line x is equal to 0, which is the y-axis, is a vertical asymptote. We're going to sketch the graph of log with a base 2 of x minus 1 and give its domain. For this graph, with a base 2, remember we can always try different x and y values. So we're going to try x and y. If x is equal to, remember what goes in here has to be positive. So let's start with x is equal to 1. If x is equal to 1, we get log base 2 of 1 minus 1, or log with base 2 of 0. Right? So that's not possible, because this thing has to be bigger than 0, right? That's what this says right here. So let's try something else. Let's try x is equal to 2. Then 2 minus 1 would be 1. Log with a base 2 of 1, that equals 0. Because 2 to the 0th power is equal to 1. And then we can try other values. Log, what could we try for x? What about 3? Let's try 3. 3 minus 1. That's log of 2. 2 to the first power is equal to 2. So the answer is 1. And we'll try one more number. Log. You have to see the pattern here. A number that would work is 5, because 5 minus 1 would give you 4. And log with a base 2 of 4 equals 2, because 2 squared is equal to 4. So when x is equal to 5, y has to equal 2. So there we're going to have 1, 2, 3, 4, 5. And we're looking at 2, 3, and 5. 2 comma 0 is on the point, is on the graph. 3 comma 1. And 5 comma 2. Okay. And remember that we couldn't type in x is equal to 1, so that's a vertical asymptote right there. So it's just the graph, the same graph that we had before where the vertical asymptote was x is equal to 0, only it's shifted to the right 1. That's what this subtracting 1 does. X minus 1 is going to move it to the right 1. Some properties of logarithms. When we take the log with some base of two things that are multiplied together, we can separate them with a plus sign. So we can say log of x plus log of y instead of log of x times y. So multiplying on the inside is the same thing as adding, right, the logs on the outside. Likewise, log of x divided by y is log of x minus log of y. So here the division should tell you to subtract. There's an exponential rule that says log of x to the r, you have some x to some r, is the same thing as taking this r and writing it down in front. R of log of x. R times log of x. Log of any base, it doesn't matter what this a is, of 1 is always equal to 0. And again, remember, this is by the definition, because this means a to the something is equal to 1. Well, the only thing you can raise it to give you 1 would be 0. So this has to be 0. That's what this thing means. Log of any base, log with any base of that same number is equal to 1. And again, remember, that's because of the definition. This is a base a is equal to a if you raise it to the first power. Right, that's obviously true. So let's practice using these rules. Rewrite the following expression. We can rewrite this using first the product expression. The product rule, sorry. This is log of 9 plus log of x squared. Right, because this is 9 times x squared. We can separate it with a plus sign. This right here, actually, you could leave it like that, but we can even do something a little bit more. This is log of base 3. Remember that 9 is 3 squared. And this right here we can write as log of x, and what can we do with this 2? We can bring it out in front to write it as 2 log of x. Same thing with this 2, we can bring it out in front to write 2 log of 3 with base 3 of 3 plus 2 log x. And remember, this is this rule right here. If the base and the thing you're taking the log of are the same, then this is equal to 1. So this is equal to 1. So this might as well say 2 times 1, or 2, plus 2 log x. So instead of something that's complicated, we just have something, I forgot the 3 here. There's supposed to be a 3 all throughout. 3, 3, 3, 3. We have something that's not as complicated, right? We got rid of we got rid of the 9, we got rid of the x squared, etc. Composing a logarithm with base a and an exponent with base a gives the identity function. So if you compose two functions with the same base, then you should get the identity function. In other words, if you have a function log of base a of x and g base a to the x power, and if you compose them in whatever direction, f of g, in other words, plug in g into f, or g of f, in other words, plug in f into g, you should always get just x out of that. In other words, taking log with a base a of something that already has a base a will cancel out the bases, and you're left with just the x. Or taking an exponent with a base a and raising it to the log of a base a will cancel out the bases, and you're left with just an x. So we're going to try to simplify this right here. How does this simplify? Again, the bases cancel. It's going to just equal 44. That was easy. Common, natural, and other logarithms. The common logarithm has an understood base of 10. In other words, log of the base 10 is just called log of x. We don't need to put the 10 down. If we just say log, we understand it's base 10. The natural logarithm has an understood base of e. So and we say that's ln of x. So if you see ln x, all it means is log with a base of about 2.72. Remember, that was 2.7271, some long number, or never-ending number. But instead of writing that in your calculator, we'll use ln x too, or log x, to mean those two same things. So let's try that. Find log with a base 10, see, but we don't write it, of 100, and log with a base e, but we don't write it, of 27. Let's try that on the calculator. We had log of 100. Notice we have the log button here, so we just hit log 100. We don't have to worry about the base. It's 2. And then the natural log of 27. There's the natural log button underneath log. So natural log of 27. 27. Close the parentheses. Hit enter. We get 3.29 or 3.30 if we're rounding to the hundreds place. So 2 and 3.30. So 2 and 3.30 approximately. But what happens if you don't have, since the calculator doesn't have more than just log or ln x, how are you going to do a different base? How would you do log with a base of 7 of 27? Well, there's a change of base theorem. And that says that if you're trying to change the base a, you can just divide by any log, that's what this says, any log b of x divided by log of any base b, the same base, of a, where a is that base you were trying to you were worrying about. So this right here, log of base 7 of 27, is just log of 27 over log, the common log of 7. Or you could use the natural log which has a base e. You could say that's equal to the natural log of 27 divided by the natural log of 7. It turns out that it doesn't matter. And because your calculator uses both of these, you can use either one of those. So let's try that. We're going to find the log of the base 7 of 30. And remember, we need to use our calculator, so we're going to do natural log. How about that? You can do common logarithm if you want. Of 30 over natural log of 7. Alright, so let's try it. Natural log of 30 over natural log of 7. If we could type it in, 7. 1.75. 1.75. Alright, so we don't have to worry about other bases. We just divide by the natural log of that base. Applications and models of exponential growth and decay. The formula y is equal to y sub 0, this is one number, times e to the k times t, represents the amount of y present after time t, and if you had an original amount of y sub 0. So y sub 0 is your original, t is your time, and the constant k is called the growth or the decay constant, depending on whether k is positive or negative. So if you have a model that's growing, then k is going to be positive. If you have a model that's decaying or shrinking, then k will be negative. For example, if you have 18 grams of a radioactive substance that are present initially, in other words, y sub 0, and 8 years later only 9 grams remain, so at t is equal to 8, so when your time is equal to 8, only 9 grams remain, how much of the substance will be present after 14 years? How much will be present when t is equal to 14? So we have two different t's here. We have to be careful. We have to do this twice. This says that original amount is 18, and we're going to multiply times e. What is k? We don't know what k is, so we're just going to write k. The time at 8 years, at 8, we knew that it was equal to 9 grams, so this should equal 9. And then we're going to solve for k first. We're going to find k. So find k first. So we're going to divide both sides by 18 algebraically. 9 divided by 18 is half, or 0.5. And how do we get rid of the e? Here we have to use one of the properties from before where we took the natural log of both sides. Why is that going to work? Remember, the natural log has a base of e. So if the base down here is e, then this e and that base e will cancel out, and you will just be left with k times 8. The bases cancel. Remember, we don't write e there, but it is there, and then they cancel. And here we just have the natural log of 0.5. So we almost have solved for k. We just have to divide by 8. So it turns out that k is equal to the natural log of 0.5 divided by 8. Okay, and then we still have to figure out how much of the substance is present after 14 years. So we're going to write this equation again. Y, how much of the substance is present if the original amount was 18 times e. Now we know that k is the natural log of 0.5 over 8. And they're asking for this after 14 years, so times 14. Well, let's plug that into the calculator and see what that gives us. This is 18 times e, so second e to the, and we're going to write, instead of ln of 0.5 times 14 over 8, I'm just going to write 14 times ln of 0.5 divided by 8. Close the parentheses and hit enter. That gives me about 5.35 grams. So this is approximately 5.35 grams. So it went from 18 grams to 9 grams to 5.3 grams. It's obviously decreasing. 18 is our original. After 8 years, we have 9. After 14 years, we have 5. So that tells us, that should also tell you, by the way, that k, this natural log of 0.5 divided by 8, if we wanted to find that, that it has to be negative. Right? Why don't you try that on your own and see if it comes out to be negative? It should. Okay, pause and practice this problem. How long will it take for an account that accrues interest at a rate of 3% compounded continuously to double? Remember, that's that compounding formula that we used from before, where we have the amount in an account to be equal to the original amount, and since it's compounded continuously, times e to some rate r times t. Well, we're not given the original. It just says how long will it take for an account to double. So whatever amount you put, let's just put p. E, the rate we are given, it's 0.03. And they're asking us what is the time, so we can't know that, of course. But they're asking us for how long will this p double? In other words, when will the amount be twice p? And algebraically now, we can divide both sides by p so that they cancel. So we have 2 is equal to e to the 0.03t. And here we're going to use that trick again. Take the natural log of both sides. That'll give us the natural log of 2. Here they cancel, and I'm left with 0.03t. And we're almost done solving for t. We just need to divide by 0.03. So this would give us t is equal to the natural log of 2 divided by 0.03. Why don't you figure out what that is on the calculator? Alright, you should now be ready to start homework section 6.1.